Hello and welcome to the JMU podcast of the Julius-Maximilians-Universität Würzburg. In today's episode, you hear an interview with Professor Sara Buson from the Department of Astronomy at the University of Würzburg. We talk about space and astronomy in general, about her research on neutrinos and black holes, and about her time at NASA. Due to the current corona situation, we record our interviews via internet telephony. If this results in a loss of audio quality, we apologize. We hope to return to business as usual as soon as possible. Until then, we wish you good health and all the best. Hello, Professor Buson. I'm happy to welcome you to the JMU podcast. How are you today?
Hello, Daniel. I'm great. Thank you very much for the opportunity of being here with you and with all the JMU audience to speak a bit more about myself and my research.
Great. Nice to have you. Yeah, today we will talk about space, astronomy, also your time at NASA, but also about more specific topics like black holes and neutrinos. But however, let us begin with a simple question to get started. Can you maybe remember how your fascination with space came about and what makes looking into the night sky so exciting for you that you picked astronomy as your field of research?
So honestly, I can't remember exactly when this happened because I believe I was born with it. And this is probably what all my family will tell you, actually. It's kind of strange, but since when I was a few years old and basically I could barely walk, already at those age I was looking at the sky and staring at stars and the moon, basically. And there is a funny story about this. My old aunt used to tell me that when I was 3 years old, I was very, very related to my grandpa. And what happened was that I was always with him walking on the countryside because he was a farmer, right? And he was a farmer, of course, at those times, he was not much educated. And then, anyway, I was posing to him very important questions and uncomfortable questions. Like, for instance, I was watching at the sky and asking, why is the moon right there now? Mm-hmm. And why is the moon shining now? Why is there both during the day and during the night? Why is it moving in that way? And of course, you can imagine, a grandpa at those times in the 80s, he was pretty uncomfortable with these questions. He couldn't answer any of them, of course. And mostly, he was very surprised about these questions that were coming from a 3-year-old child. Mm-hmm. So I don't know where this comes from, of course, because I was born with it. But I know that as I was born with it, I always carried it all time along. And that's where it brought me, basically, here in Würzburg, still looking for the stars with the astronomy department.
Okay, that's great. So like a natural interest for the whole research.
Yes, exactly.
Okay. Yeah, I think probably most people are fascinated when they look up into the night sky, into the stars, out into the space, basically. But astronomy allows us an even deeper look into the unknown, into the far away. We can see things we can't see with a bare eye. But it also allows us to look back at ourselves and our surroundings from the outside. Can you tell us a bit about what this look back can tell us about our place in the universe, in our star system, what makes it so special, and maybe also about our self-perception as humans?
Yeah, on this regard, I like always to think in the way that Carl Sagan was thinking about. Mm-hmm. So eventually, we are all made of star stuff, right? The ultimate molecule that our body, everything we know is built on, is built thanks to the star activities, basically, our activities of extreme explosions that happen in our universe. For instance, he used to say that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, and the carbon in our apple pies, they were all made in the interiors of collapsing stars. So from this point of view, we are not that far away, from this distant universe that we used to look at with our telescopes. So it's more a matter of where we place ourselves within this context, this universe. And the way that I like to put myself is right at the center, let's say. Mm-hmm. In the center, in the sense that there is no real center in this universe, but all the things that are hosted in this universe are special of some kind. They are special and different and unique. So that's my way of seeing it as in this distant, but so also nearby universe system.
Okay, great. And also about this position we have in our galaxy. What makes this position we have in space so special?
That's probably ourselves, right? Because we like to believe that we are special and we are the center of everything and whatever. But eventually, if you study a bit of physics and eventually astronomy, you start to realize that there is no special perspective except for the one that you are looking at. Or the other way around. There are different perspectives of this cosmos, and each one is unique in its own way. Okay, so my answer to the question, what's special about our galaxy and maybe Earth or whatever, the only thing that makes it special is ourselves. But except for that, nothing prevents, the cosmos from building or having other different Earth in all its different worlds that exist there. So the fact that we haven't observed any so far doesn't mean that it doesn't exist, of course. And this is very important, I believe, for human beings, that we should keep, as humanity, looking for things far away, even if they will probably not ever reachable for us, at least with the current means. Because, we never know, and on the other side, it's part of us, eventually.
Okay, great. Yeah, and when thinking about this, like our self-perception and space and researching space, I have to think about the depiction of space and space research in like science fiction. It often stands for like humanity overcomes its conflicts, comes together for this greater goal. And also in reality, space research is a very internationally connected field with a lot of cooperation between countries, different institutions, and so on. And you yourself have already worked in various countries and institutions, most recently at NASA or now at the University of Würzburg. When you look at this, how important is this international aspect of astronomy? And when looking, like, for example, space programs like the ISS, where there's a lot of international work happening. But on the other hand, there's also like this, in the media, it's often called this race to Mars, or like back in the 50s, 60s, the race to the moon. Do you think this space research and space travel brings us as humanity closer together, or is it more that it intensifies also rivalries between countries or institutions?
Well, then, this is indeed a very tough question because probably both things are true, right? It is a kind of race for discoveries in our cosmos. Both brings us together as humanity, and as well it intensified some rivalries. Indeed, the way I like to see it is more the former one. So the way that there is no achievement that a human being can do except for having it done as the humanity itself. Because it is what we are facing here in this it's much bigger than a single or few human beings. It's a challenge for the entire humanity. And as a challenge, it can be also very profitable for the entire humanity, of course. And in this point of view, it's very important that we are united. So it's true that, for instance, I have traveled many countries and worked with different people and different environments, etc. But eventually, I like to see myself as an astronomer belonging to the astronomy community. Okay, because this is where I decided to put most of my efforts in this life. And eventually, of course, astronomers belong to humanity. So we are doing a kind of service for the full humanity in the work that we are doing. There is, of course, the other part of your question that is regarding rivalries. And of course, this part as well of the human being, right? Because we like it's the challenge of discoveries and being the first one to see these things that also pushes us to supersede some limits as well. But personally, at least for myself, the way that I like to do this type of work is a challenge together with the other people who are taking the challenge with me. And no rivalries, basically.
So, cooperation.
Yeah. I strongly believe cooperation should be always the strong fundament of anything when it comes down to humans, because, of course, when it's easy, when we look to ourselves from Earth, You can see many powerful men and people or women, right? But then when you take this pale blue dot, the Earth, and you place it in the immense vastity of the cosmos, well, we are nothing, right? What is this big man doing on Earth when you put it in the cosmos? By himself, nothing. So maybe if he joins his effort with all the other people, maybe he can do a tiny bit more, that he can have a bit more impact, let's say, although it's still a huge word, impact, but impact in our universe, at least from the point of view of exploration, let's say.
That's a beautiful perspective. Yeah, I already talked about your time at NASA. It's an institution probably everybody knows or at least has had heard of, maybe in articles, discoveries, space programs, moon landing, but also like there's this public image database of all this space photography they are doing with their telescopes. It's a lot of in movies and even in fashion we start to see the NASA logo over and over again. Can you maybe give us a bit of an insight into like the world of NASA, if I can put it like that? So what was your everyday life there and what drives people who work there?
Oh, yeah. So indeed, I was kind of surprised, but also very excited when I was picked to work at NASA. Specifically, I worked at the Goddard Space Flight Center, which is nearby Washington, D.C. And that's the center where most of the astrophysics science is carried out. Okay, so you will run in a bunch of astronauts there, but it's not really where they are doing their main business. You have to go down to Cape Canaveral or other places to meet astronauts that are training. But indeed, it's a very exciting environment to be within. The people that are there, most of these are all great people, scientists, I mean, that in a way or in another, they have made great accomplishment in the field. And one thing that I really highly appreciated there was, for instance, the ability to be in your own office by yourself, but anytime you would have the most difficult question or the most dumbest questions in science, you would always have the right expert next door, basically. If not next door, it was on the floor above you. So that's great. It's indeed a kind of unique environment. There are certainly other communities like NASA elsewhere as well in Europe. That's but indeed, my experience there, I had the luck to experience this at NASA, and it was simply great, of course. Regarding the everyday life, maybe it's kind of boring because probably like most people at NASA, I'm really devoted and enthusiastic about what I'm doing, right? So most of my time I spend it working, which probably is the right thing to do there. But yes, working and then, of course, interacting with people nearby. It's great because, as I mentioned, you can exchange ideas quite easily with anyone, not only people strictly related to your research field. And that's the power of such environment, right? When you are exposed also to other fields of research, I believe that's where we are able to make the biggest progresses. Because we are able to tie together all the pieces of the puzzle. It is cosmos, right? Yes, at NASA I had very great people to work with.
So it basically has this cooperation thought again, like all these experts in one place and everybody cooperating. Yeah.
Cooperation indeed was very good there. I can't hide that there can be also a bit of competition, of course.
Of course.
But I mean, that's normal, I would say, because when you want to excel in something, I mean, competition is part of the game, right?
Sure.
But at least from my experience, I never face it as a too much negative aspect in my life there, let's say.
Okay.
I had always the opportunity to use it in the right positive way.
That's great. So yeah, you already talked about you worked a lot, and this resulted basically in your research at NASA. And this research had to do with neutrinos and black holes. And before we dive a bit deeper into those topics, maybe we should discuss these terms a bit individually to understand what we're actually talking about. And I would like to start with black holes. And probably most people have heard of them. And if I start from my point of view, there's probably some knowledge, a lot of false knowledge, and maybe also some fiction about them. Can you maybe briefly explain what are the most important findings we have about black holes and also what makes them such interesting research objects?
Black holes are quite fascinating objects. Maybe I'm biased a bit because it's my field of research, but from my experience, many people, of course, are fascinated as well. So there must be indeed something interesting to study here. So one important thing to keep in mind when we talk about black holes is that such exotic things that exist in our universe. Mm-hmm. But they are rather quite common things that pervades our everyday life, let's say. Let me explain it a bit better in simpler words. Mm-hmm. What we believe as astronomers nowadays is that each galaxy at its center is hosting a black hole. Okay, so any galaxy that you look up in the sky will have very likely a black hole at its center. So this is telling us that it's a quite ubiquitous system, powerful system in our universe. Okay, so it's something that happens pretty often, and it's also related to galaxies themselves. And of course, in our own Milky Way as well, we have a black hole, we believe, and that's hosted in the center of the Milky Way galaxy. Basically, if you look up in the sky, you look for the Sagittarius constellation, and within those stars, you will find the center of our galaxy. Mm-hmm. And that's also where the Milky Way black hole is located. So most of galaxies, then they have relatively light black holes, let's say. In this sense, the black hole mass is more or less at the same size of our sun, let's say, mm-hmm. the mass of our sun. That can seem already quite heavy, from the human perspective, but going back to our overall perspective in the cosmos, that's not really the case. Mm-hmm. Because we know nowadays that there exist supermassive black holes. Okay, these supermassive black holes, sometimes I like to dub them also monsters black holes, because these are pretty rare, quite rare to find, let's say, in our universe. We believe that about 1% of galaxies are hosting such type of black holes that are extremely heavy. And when we say extremely heavy, you can imagine to have 10 to the 8 times the mass of our sun, all congregating in one single point. Mm-hmm. And that's the supermassive black hole that we are talking about, okay? So indeed, on a human scale, that's unimaginable, of course. But going back to black holes, yes, these supermassive black holes are pretty rare systems. And anyway, we already have found a lot of them. So they are rare from the cosmic point of view, but then, of course, there are many more that can be found when we use our powerful telescopes. What makes them so interesting is probably the fact that they are extremely powerful. Or better, they are capable of, at least in some cases, they are capable of accelerating particles at extreme energies. And of course, when we say extreme, that means, what I mean is that we as humankind are not able to reproduce such systems. On Earth, we have built extremely powerful accelerators. You probably are familiar with those. One, for instance, is the Large Hadron Collider in Geneva. It's from CERN. And that's so far the most powerful particle accelerators that is available in our hands. Okay, still, if we use such an instrument, we will never reach the power of these particles that are accelerated in black holes. Mm-hmm. And this basically brings us to a dead-end question, right? So we believe we are smart, so we are able to understand quite nicely the physics, at least on Earth. And then, therefore, we have built this extremely powerful accelerator, but still we are behind when we look to the cosmos. The cosmos has been able to produce supermassive black holes that are accelerating particles at much more powerful energies than what we are able to produce on Earth. So how is this possible? Mm-hmm. This is one of the questions that myself, of course, with a large team of experts in the world, are trying to address. And let me also say, it's not a new question. It's a long-standing question since centuries, basically, since when we discovered this type of black holes. And the hope, of course, is that at some point someone will be able to answer it. But unfortunately, at the moment, we have, of course, very good guesses, but still we are lacking the definite clue to understand the physical mechanism here. So indeed, I believe they are extremely interesting objects. And I hope, even if at the moment they have no immediate turnaround, let's say, in our everyday life, I hope in the future they will have as well, so that we can use this science also for something more practical, let's say, as other people like to think.
You said there are some very likable gases. Is there maybe one which has like a lot of researchers that say, okay, this is maybe the thing? Or
maybe let's say the other way around. So we have excluded many other theories, so we are left with a couple that are the most likely ones. But of course, most likely still doesn't mean that we understand completely the system, right? And we haven't started from the right hypothesis. And for this reason also, maybe we can connect straight away to the next questions that you likely want to ask me, that is about neutrinos. Yeah.
So yeah, basically to maybe state it, the next question would be basically, what are neutrinos and what are they doing and why are so interesting in astronomy and also in the context of black holes?
Yeah. So the point is that, of course, we have studied black holes since a long time. And we have exploited a lot of tools and means to study them, but still we are lacking the full evidence for the process that is the processes that are involved, let's say, in the creation and as well in the mechanism that is powering these systems. So in the last century, what scientists are trying to do is to use different means to study these astrophysical objects. And when I say means, that mostly refers to particles. For instance, we are mostly familiar with photons, right? The sunlight, for instance, are photons. The radio waves that we are listening now during this time that we are speaking, these are photons. When we go to the doctor, to the hospital to get an X-rays are photons as well. And all these are a mean that we are quite familiar with. Humankind has been using photons since a very long history. What happened is that recently, in the past decades, we were able to build different instruments that are capable of catching different type of particles. Certainly, you have heard about the discovery of gravitational waves, for instance, from the LIGO and Virgo detectors, which I will not talk about today, of course, because it takes too much time otherwise. And the other important instrument that has been coming online lately, for instance, is IceCube. That is a neutrino detector located in the South Pole. So neutrinos are extremely light particles. Extremely light means that basically we are still not able to measure their mass. We only placed upper limits. So we say it must be lighter than this, otherwise I would have measured it. And besides being very light, they are also neutral particles. Neutral means that they are chargeless, and therefore they will not interact via, for instance, electromagnetic mechanism, right? So this makes them kind of unique particles in our cosmos for two reasons. One is the kind of good reason. So since they basically barely interact with matter, the only interaction they can have is when one of such neutrinos will literally crash into another atom. Okay, when this happens, then we are able to detect the neutrino. So the fact that they do not like to interact with matter makes them unique messengers, as we call them in astronomy. Because basically, from the time that they are born in the astrophysical system very far away, and the time that then we are able to detect them on Earth, they will have traveled almost unimpeded through all the cosmos. So, said in simple words, if we detect a neutrino and we are able to track back the path that it traveled, then we are able also to know the origin of these neutrinos. And just to put into context, for photons, this is much more difficult. And also for other type of particles that we are able to detect in our cosmos, for instance, cosmic rays. For these particles that are as well produced in these astrophysical systems, the game is a bit more complicated because both photons and cosmic rays, they would interact with material that they travel through. You can think about intergalactic magnetic fields or simple stars in galaxies, etc. And these interactions most of the times prevent us from observing directly the origin of these particles. So neutrino on this side, they are much better messengers because, as said, we can just get a neutrino on Earth and straight back look where it comes from, and then yet you got the origin of the neutrino. So you got the astrophysical source.
And that's basically what you did in your research, follow back neutrinos to a black hole? Yes,
that's exactly what we try to do at least. We got a so-called alert from this ice cube detector. So our colleagues from the ice cube team, they informed the astronomical community that they observed these high-energetic neutrinos. And that for us means that it's very likely that it was originating from the cosmos. And what we did then was, of course, look back from where it comes from and check with our instruments if we were able to see something special about that region of the sky. And that's what's happened basically with the work that I've done together with collaborators. What we found out was that very likely the origin of these neutrinos was a supermassive black hole. At least it was originated within the galaxy that is hosting the supermassive black hole. And also it's not only the supermassive black hole itself. This type of galaxy belongs to a special type. We call them active nucleus. And in these galaxies, sometimes what we observe are jets of relativistic plasma that are emitted right from the center of the black hole to very far away distances. Mm-hmm. So what we are arguing in our discovery work is that it's possible and also likely, let's say, that this neutrino was originated within this relativistic jet of particles.
Mm-hmm. And can you already tell what this discovery means and what we can learn from this, or what you can understand about the universe from this discovery?
Yeah, so the discovery by itself may seem a bit limited because, of course, you may think we have discovered just one neutrino source. Mm-hmm. And, of course, likely there are different types of neutrino source populations that we still are not aware of. But maybe the main question here goes back to neutrinos and photons, what we can learn from tying together these two messengers. Mm-hmm. And the picture is much more broader. Mostly what we can do with neutrinos and photons is trying to tie this picture together with the one of cosmic rays. So now I'm bringing a new player in this game. Cosmic rays, those are charged particles, typically, for instance, protons or heavy nuclei, that we do know exist in our cosmos. We do know they are accelerated somewhere. And we know this since at least 100 years. It was I think, in the early 900th century, the past centuries, when Victor Hess, the Austriac astronomer, he was the first one to be able to see these cosmic rays and to say that these particles were not originating from Earth, but they were rather originating from far deep into our space. Mm-hmm. So this discovery happened 100 years ago, and since then, actually, we haven't moved that far because we still do not know where they are originated, and we do not know the exact composition and many other things. And cosmic rays are very important for humans, actually. Maybe not everyone knows that cosmic rays would have the power to completely destroy, wipe out the life on Earth if they were able to reach the Earth ground. Mm-hmm. Because they are very powerful, okay? But luckily for us, we have the Earth atmosphere, mm-hmm. and also the magnetic field, and all these together serves as a shield for humans and every type of life on Earth.
Okay.
It serves as a shield from cosmic rays that therefore are basically, let's say, broke down by the time they reach Earth, because of course they will go through the atmosphere, but they will lose energy doing this. And by the time they reach Earth, and then our body, for instance, they are much less powerful and they will not harm us. And that's the only reason that, that's one important reason for which life can exist on Earth. Again, looking the other way around, so we are happy on Earth, we are safer, and we do not have to worry about cosmic rays. But on the other hand, going out into space, we do have to worry about cosmic rays because we do not have the magnetic field, we do not have the atmosphere, and we are completely bombarded by this radiation. So it can be also important to understand where this radiation is coming from, and most importantly, understanding how the physical mechanism that is originating this radiation. And as mentioned before, we know this radiation since 100 years at least, but still the information that we get from these cosmic rays alone are not enough to understand completely this type of radiation. So what we can do, at least to improve our knowledge in this, is bringing together other information, other pieces of the puzzle. And we can do this, for instance, using the photons and the neutrinos. And in my case, what I'm trying to do is using these messengers, neutrinos, photons, and eventually cosmic rays, in the context of black holes and active galactic nuclei, these type of sources that I'm mostly working on. Probably there is a good bet, let's say, out there that these active nuclei could be the origin, at least of part of these cosmic rays. And therefore, that's where I took my bet. I'm trying to study a bit more this part, and I hope to get some results, at least at the end of my huge project that I just got approved from the ERC.
Okay, and maybe to also understand a bit what you are actually doing, can you tell us a bit about the practical work and maybe also all the time that is spent for such a discovery?
Yeah, well, first of all, being at Würzburg, as you introduced myself, I'm a professor. So indeed, an important part of my job here is teaching and hopefully share my excitement on this research with the students. So among my top priorities, there are, of course, teaching and mentoring young scientists. For the research itself, I do not spend much time on the telescope because what I'm doing actually is mostly space science. So I'm utilizing telescopes that are out into space. The one with which I'm mostly working with is the Fermi Gamma Ray Telescope that was launched by NASA in 2008. And the good part of this is, let's say, that NASA takes care of most of things. So they would, take care that the telescope is operating safely and producing good data all the time. And in this way, the only thing I have to worry about is my research. So I can easily take this data that are publicly available and look at my favorite science topics with this data. So the actual part of the work is on the research side is, of course, a lot of data analysis. But before that, you have also, of course, to study the topic and you have to make the right guess. So you have to be aware of what you are looking at and what you are looking for. That's very important because without interpretation, the data themselves, they cannot speak, right? So on the one hand, it's important to have some knowledge and familiarity with the data analysis part. But indeed, scientifically, knowledge of the topic is the base for any good research work. And regarding, you were asking about the time behind such a discovery. Well, there is a lot of time. It's not just my time at NASA, of course. It's been at the time that I spent as a student. I was initially at Padua in Italy. And I do remember, I always have been fascinated by this type of science, which implies a real commitment all the time, because you never know when the right discovery is coming. Or better, you never know when what you are looking for might come. What I do is mostly real-time analysis. That means that the telescope is taking data, and as soon as they are downlinked to Earth, there is somebody that has to look at those data and make sure that we are not missing anything challenging and important, right? And that's what happened, for instance, in this case. There were colleagues who looked immediately at our data, the LAT telescope data, and we found out this coincidence between the neutrino from Ice Cube and a gamma ray source from the Fermi-LAT catalogs. And in my case, this type of research, it's very important to be also continuously committed to what we are doing, basically. So yeah, time is an important part, commitment too.
Okay, so it's basically not one project after another, but also step for step in projects connecting to each other, if I understand this correctly.
Yes, totally. Because most of it is due to the fact that before being capable of having enough familiarity with the task, with the topic, you need time. And that means also that you have to sort of specialize on something, right? There are probably some scientists that are able to do everything. I'm not that kind, unfortunately. And so what I do is I studied hard my topic, let's say, and I try to be among at least the best people that are doing this. And in this case, yes, you need a lot of time. And as I mentioned before, also bringing all together the pieces of the puzzle. So it's not just one isolated step by itself, but it's more looking at the broader picture and understanding where we can get 5 years from now, 10 years from now. Also because nowadays, the science I'm doing is with instruments that are available nowadays. But as scientists, we also want to do better always. And so we are looking further and we are building new instruments, for instance. And to do this, you want to be sure that you are putting the efforts in the best thing that you can think about. Simply because the efforts are limited, right? And when I say efforts, indeed, I mean also money, funding.
Of course, yes.
Agencies, yes, they want to fund science, but they also have a lot of requests for this. And therefore, you have to be good also in letting people understand why your science topic is so important that it needs to be promoted instead of another one, unfortunately. So in this sense, the broad picture is very important too.
Okay. Yeah, you seem to be very successful with that because you recently received an award from the European Research Council and also a starting grant for your new research project here at JMU. And this basically also, like we already talked about, follows up your last research. And you are still working on neutrinos, black holes. Can you tell us a bit about this project, where you currently are, in which state you are, what the next steps are, and basically what the goal of this current research project is?
So the starting grant that is awarded by the European Research Council is one of the most challenging grants to achieve, basically. The success rate, is about 10%. So as well here, I was quite surprised, but of course I'm used to be awarded of this. Certainly, I put a lot of effort on it, so I'm happy that the work that I've done has been recognized. Because besides the money, in this case, it's a pretty consistent grant. It's 1.5 million euro that can be used entirely for the research project. But besides that, I feel like also honored because it's, of course, an endorsement from colleagues in my research field, experts, people that, of course, I respect. And they have considered myself as a scientist capable of conducting research at the extremely high level. So, it is very honorable for me, at least. So the research project, as you were mentioning, is still about neutrinos and black holes and, of course, active galactic nuclei. And the idea here is to dig a bit more about on this potential discovery that we have done with collaborators relating this ice cube neutrino, the high energy neutrino, to a black hole hosted in an active nucleus. The point is that the discovery by itself is very interesting, right? Because it's the first time in history that we were able to connect these two information together so nicely. But again, to make a big claim, we need also big evidences, again, as Carl Sagan liked to say. And in this case, I took it literally. So we have the clue that one source could be potentially the source, the origin of these neutrinos. But out there, we have thousands of these sources on one side. On the other side, we have a lot of neutrinos that we are for sure not able to connect to each of these sources. So the challenge that I took over with my project is to understand what fraction of neutrinos we are able to connect with this type of black hole sources. And hopefully also the main goal will be to find an uncontrovertible evidence for the connection between neutrinos and these galaxies that host a black hole at the center. Because as I mentioned earlier, we found a hint for it, this discovery, but that's far away from placing, a strong statement saying that we have discovered at high confidence the origin of all neutrinos. We are still behind here, but we have some promising way to go through, and that's where my project is going to be heading over, basically.
Okay. And can you tell us how far are you currently? Are you still in the beginning, or is there?
Yeah, unfortunately, it's far the beginning, I would say. I was informed about the grant basically a few months ago. That was in September 2020. And then, of course, as happens always with this type of grants, there is a lot that has to be done. Not only for the science part, which, that's quite clear to me. I wrote it down, so I know already what's going to happen step by step. But such type of grants that are pretty large, they also require some level of organization. I have, of course, several collaborators on board with me that will be certainly helping a lot in different tasks. And as well, I am aiming also to build a group, a team that will help me trying to solve this question, because I'm not going to do it alone, of course. So as a starting point at the moment, I'm looking to enlarge my team. So kind of fighting, let's say, with bureaucracy, if you want to put it that way, which I have to say, honestly, at Würzburg University, so far, I've been very happy, because the people that have been supporting me are doing their job very, very well. And that helped me a lot, because, of course, I'm a scientist. I'm not meant to know about bureaucracy. You might have guessed, for me, it can be also more challenging, because I'm not a native German speaker. So I'm familiarizing with German, but indeed, most of the bureaucratic forms comes in German. So that's also an additional challenge. But if I will stay in Germany for a long time, I plan also to definitely learn and be able to speak a fluent German. That's my aim and the goal here.
Okay, then we're coming to an end of the interview, but maybe to close this with a more general question, and also to make a connection to the questions in the beginning. Like space research, like many basic research fields, are regularly criticized, so to say. Like they are expensive without any applicable or practical results, and I guess it's not that easy, because there's definitely more to it. And from your perspective, can you tell us about why is it important for science, but also to humankind, to understand the universe, how it works, how things are connected?
Well, I believe the answer is pretty simple, and it was already given by others. And the answer is, if you want to make an apple pie from scratch, you must first create the universe, right? Without the universe, you cannot do your apple pie. And so it was just a funny sentence, of course. But it's just to say that indeed, as I was mentioning earlier, the science that I'm doing, the type of work, the research, it can be pretty far away from everyday life. But that's, again, mostly because most of the times our perspective is limited to the everyday life, and we do not look that farther away. For instance, some years ago, nobody was talking about going to Mars or going back to the moon, right? But nowadays, this has begun to be quite a talk in the community, and not only the science community, but also the business, the economic community. Because if you go back to the moon, or for instance, go to an asteroid, there you can find pretty rare minerals or chemicals that can be quite useful on Earth. Okay, for instance, and things that you cannot find on Earth as well. Just to say that we never know where the goal that we are going to reach if we look only pretty close to us. And it's only having a broader perspective that instead we can really have major improvements in our everyday life. And in this sense, again, for instance, if we want to go back to the moon, or we want to travel to Mars, or eventually we will be able to travel even within our galaxy. Well, in that case, wouldn't it be nice to know the weather conditions out there? And when I say weather conditions, I'm trying to connect again back to my science. I was mentioning earlier that cosmic rays are pervading the universe and our galaxy itself, right? And as soon as we go out our atmosphere, then we have to deal with cosmic rays, right? So what happens to our astronauts when they are going to go out into space, into their shuttle, for instance, or the spacecraft? They will be completely exposed to this cosmic ray radiation, right? And still, we do not know much about this radiation. So wouldn't it be nice to be already aware of the weather condition out there before going out there? Mm-hmm. Right? If it's winter, we want to know that outside it's cold and we need our jacket. So similarly, it's for our astronauts and ourselves as well, because at some point, I believe it will be certainly much more common also for anyone to travel into space. Space tourism already has started as a business. Mm-hmm. So again, looking so close in everyday life, yes, the work we are doing as a scientist, in my case, for instance, are not much useful. But certainly it will be useful, I believe, for next generations, when things that we are not able to conceive nowadays will certainly exist. And hopefully also they will have a beneficial impact in our humanity.
Mm-hmm. Okay, that's some great closing words, I would say. I thank you very much for your time and the knowledge you shared with us. And of course, I wish you all the best for your new project, for all the bureaucracy. And would like to say thank you, goodbye, and until the next time.
Thank you, Daniel, and thank you everyone for listening.
Thank you very much. Bye-bye.